All right, let's just jump right in with a statement that probably sounds completely wrong. I know what you're thinking, because we've all heard it a million times. Nothing can travel faster than the speed of light. It's the ultimate cosmic speed limit, period.
And yeah, that's a perfectly fair question. For the longest time, impossible was the right answer. But it turns out the universe is a whole lot weirder than we ever gave it credit for. And this isn't some brand new, shocking discovery. It's actually the endgame of a huge debate that started almost 100 years ago, a debate that pitted the biggest brain in physics against his own groundbreaking theories.
You heard that right. Albert Einstein, the very man who came up with the cosmic speed limit, was the first one to realize that this new theory, quantum mechanics, seemed to shatter it. He saw a massive contradiction, a fundamental clash, and what came next was basically a battle for the soul of reality itself.
So to really get what this whole fight was about, we first have to appreciate what Einstein was so desperately trying to protect. You see, his entire theory of relativity, everything, is built on one absolutely crucial idea.
And that idea is called locality. It's one of those things that just feels like pure common sense, right? If you want to push a chair, you have to actually touch it. An event that happens right here can't instantly cause something to happen on the other side of the planet. The influence, whatever it is, has to travel, and its top speed is the speed of light. This isn't just a nice thought, it's the glue that holds cause and effect together.
So think about it this way. If the sun were to just poof, disappear right now, we wouldn't know. We keep orbiting like nothing happened for a full 8 minutes. That's how long it takes for the news, the gravitational ripple in spacetime, to travel from the sun to us. Without that delay, you get all sorts of paradoxes where effects could happen before their causes. The universe would literally break. For Einstein, locality wasn't just a rule, it was sacred.
But then along came quantum mechanics, this bizarre new theory describing the fuzzy, weird world of atoms and particles. And as Einstein dug into its rules, he found something that seriously freaked him out, something that seemed, well, non-local. So at this huge physics conference back in 1927, Einstein stands up and presents this thought experiment. He says, imagine you've got this electron. Quantum mechanics tells us it behaves like a wave of possibilities. When you finally detect it, say right here at point A, that whole wave of possibility instantly collapses. The chance of finding it over at point B, no matter how far away that is, drops to zero in the exact same moment. For Einstein, this was a massive red flag, a total violation of locality. How could a measurement here instantly affect what's happening way over there? This is what he famously called spooky action at distance. And for him, it was a sure sign that quantum mechanics wasn't the full story.
But the other guys, the quantum pioneers like Niels Bohr, they had a totally different take. Their view, which we now call the Copenhagen interpretation, was basically, hey, the math works, it makes perfect predictions, so just accept it. Our job isn't to say what nature is, it's to predict what we can measure. To them, asking what the electron was doing when no one was looking was just a meaningless question.
Einstein just couldn't stomach what he called this tranquilizing philosophy. So in 1935, he teamed up with a couple of colleagues, Podolsky and Rosen, and they came back with an even stronger argument, a real knockout punch designed to expose the problem once and for all.
And this new argument was built around something we now call quantum entanglement. You can think of it like creating two particles that are linked, like two sides of a single coin. If one is heads, you know instantly that the other one is tails, even if you've sent it to the other side of the galaxy. And this is where the two explanations really go their separate ways. Quantum mechanics says the particles are in a fuzzy, undecided state. When you measure particle A, you actually cause particle B to snap into its state. That's the spooky, non-local connection. But Einstein offered a much more sensible local idea. He said, no, it's like putting a left-handed glove in one box and a right-handed glove in another. When you open a box and find a left glove, you don't cause the other one to be a right glove. It always was. You just found out the information that was already there.
So for decades, this was just a philosophical staring contest. Both theories made the exact same predictions for every experiment you could think of. There seemed to be no way to prove who was right. And then, in the 1960s, a physicist named John Bell walks onto the scene.
Bell dug up Einstein's old argument and realized that there was a way to settle this whole thing. He designed a test, a clever twist on the original experiment that would finally force Einstein's hidden gloves theory and the spooky coin theory to make different, measurable predictions.
The twist was so simple but so smart.
Instead of just measuring one property of the particles, the observers would each randomly choose one of 3 different measurement settings, like 3 different angles to check. And the crucial question was this: when they happen to choose different settings, how often are their results going to disagree?
And this is the beautiful part. This is the fork in the road. Bell proved, with math, that if Einstein's local, common-sense reality was right, the results had to disagree at least 1/3 of the time, 33.3% or more. But if quantum mechanics, with all its spooky non-locality, was correct, the disagreement rate would be lower, exactly 25%. It was a clear prediction. Nature had to pick one.
So the stage was set. This wasn't about philosophy anymore, it was about doing an experiment. All that was left was to actually build the thing, run the test, and ask the universe itself which theory was right.
Over and over and over again, in more and more precise experiments, the answer came back. The disagreement rate wasn't 33%, it was right around 25%.
I mean, just look at this chart. The results were crystal clear. Every single time, the universe sided with the spooky, non-local predictions of quantum mechanics. Einstein's more intuitive, sensible picture of how the world works was wrong.
John Bell himself summed it up perfectly. He said the experiments basically force our hand. We have no choice but to accept a reality where what happens here can, in some strange, faster-than-light way, influence what happens over there.
So what's the bottom line here? It means Einstein was right to be worried. Quantum mechanics really is non-local. But his conclusion was wrong. The spookiness isn't a flaw in the theory that needs to be fixed. It's a fundamental feature of reality itself. In fact, Bell's theorem proves that any future theory that ever hopes to describe our universe correctly must have this faster-than-light connection built into it.
But wait, is there any loophole? Any possible escape hatch that could save Einstein's beloved principle of locality and still explain why the experiments turn out the way they do? Well, there might be one, but it's going to require an even bigger, more mind-bending leap of faith.
What if we just get rid of the collapse part altogether? There's an idea called the many worlds interpretation, and it suggests that when you make a measurement, the universe splits. In one universe, you get one result, and in another universe, a parallel version of you gets the other result. In that view, there's no spooky action, because both things actually happened. It's a truly wild idea, but it would mean Einstein's dream of a local reality might not be dead after all. And that leaves us with a pretty fascinating choice. Do we live in a universe with faster-than-light influences, or do we live in one with an infinite number of parallel worlds?